please. Hello, test, 1, 2. All right, yeah, the Swedes are happy, and I hope you too. Okay, we're gonna have a nice presentation from Erdgeist and Frank, and it's about flash memory. As you all know, flash memory skyrocketed from 128 MB to 8 GB, and that's incredible. And they're gonna talk about some security issues. Thank you, and a warm welcome, please.
Okay.
Hello? Oh. I think I got a slide from the wrong talk.
Okay, so who of you has seen the previous talk on Linux memory dump extraction from keys? Okay. We are here to tell you it's even worse. The main topic of our talk will be the issues that coming up with flash memory, but first we will do a little bit of introduction why we care about this. So the secrets that you store on your computer can be roughly divided into two things. One is the real secrets, the stuff that you really want to hide, usually known as clear text, and the other is the stuff that you need to use to hide your clear text. That's basically then keys, passphrases, and everything that has to do with that. Surprisingly, most people have a high confidence in their passphrases. So they believe that their passphrase that they're using is probably good against dictionary attack or whatever. But if you look at it from a cryptographic point of view, almost all passphrases of lengths that you can still memorize have a way too low entropy. So basically, if you think as the passphrase as the input into your crypto algorithm as the key, then you will never reach any length of key that you would like to use in a crypto algorithm, meaning the passphrase is the weakest link. So even if you generate by salting and everything a key from a passphrase that is reasonably long, the core entropy that is inside the passphrase is way too short, which is why we have all these nice external devices with chip cards and so on, to make the process of attacking the passphrase more complicated. But that's essentially it, making attacking more complicated. Passphrases are also victim to all kinds of other issues like shoulder surfing, somebody looking over your shoulder, somebody listening to the sequence of your keys clapping, everything. So key sniffers and so on. So the issues that we need to look at is where are your secrets, meaning the clear text is hidden, and where are the means of hiding your clear text are processed and stored. And both of that is going to change with flash memory going into all kind of devices.
So in order to use your secrets you use to protect your clear text, you have to enter and well, sometimes display your passphrases and passwords. And like heard in the talk before, those passwords have to pass through well, kernel buffers, keyboard buffers. They will be displayed. They can be cached in graphic card memory. If you use smart cards, there's also always dumps of that memory in kernel buffers. So you always have to be aware of which path your clear text and your passphrases take into the kernel buffer and to the user interface. And you have to make yourself clear, to remind yourself that the memory is being copied over and over again. So the scenario is a stolen device. Someone has stolen your telephone or your PDA and wants to retrieve data that's stored on it. And as a programmer, you use well, system call, libc calls like malloc and realloc to allocate your memory and store your values. And you usually don't care what happens with that values when you free them, or even you realloc them. some implementations, or most implementations of malloc or realloc actually use two ways to get the memory to store values in. For smaller buffers, they have for each power of 2, they have dedicated pages where they store the memory allocated. So if you resize your allocated buffer, it is guaranteed to be copied from one of those pages to another, leaving lots of copies lingering around. And most implementations, if not forced to, don't mind to erase the memory after they take the copy, and free call most often doesn't even erase it to, well, under FreeBSD and under macOS there's options in etcmake.conf or in environment variables to force the malloc implementation. Well, the free to erase the memory under ptmalloc 2 and diet-libc malloc, there is as of today no way to do it. So we have to be aware that well, that does not only apply to your passphrases and passwords, but does apply to your clear text as well, that it's being copied around over and over. For larger memory, the most malloc implementations use the mmap feature, the mmap feature, to allocate pages, so the memory is not actually copied around, but it's still there if you free it. So.
Okay, another issue that will slowly lead us to the upcoming disaster is flash memory. If you keep stuff in normal memory, it may burn in. So the last scientifically published paper on memory burn in the open literature is still the stuff that Peter Goodman did a couple of years ago. Essentially what happens is that the refresh cycles in normal memory cause a slow burn into the memory cells, meaning that if you're doing a real low-level forensic on the memory cell, it's not only still there after 30 seconds or whatever, but it may be still there even much longer. So there are forensic techniques with low temperature, meaning that they can freeze memory before powering down or shortly after powering down. But for instance, on devices where keys are stored and where the memory region where the key is held is never changed, then the key may slowly burn in. This is basically the same effect that you know from our old monitors. When you always display the same image, then the image is, a ghost of the image is burned into the tube, and the same effect happens into memory cells. So the thing that is strongly recommended if you're handling crypto keys in memory that are going to be there in the same position probably for quite a while, it's something that's called bit flipping, meaning that you're XORing the key in intervals maybe of a minute or 5 minutes or whatever your power consumption allows, to prevent the cells from being stuck. So, but that's only in normal memory.
Well, and then of course you have problems that the operating system confronts you with. It's swapping out portions of your memory to the disk if it is not used. You have ways, running as root. You have ways as an application to prevent certain memory areas to be swapped out. If you're a userland program without root rights, you may not do it, like mlock under POSIX and virtuallock under Windows. And even on a normal hard drive, being swapped out is not cool, since you're never guaranteed that the device your memory is being swapped to is a local disk or is a disk at all. So the way to prevent your secrets leaking there would be to use swap encryption with drawbacks you heard in the last talk. But well, swap memory is seldom found on mobile devices. So you're going to abstract the problem of protecting and securely erasing your memory by encrypting it, and losing the key if you intend to erase your data securely. So you narrow down your problem on losing a few bytes, and you can abstract the problem from shattering a whole hard disk to just losing a few bits. And you usually use a stream cipher to create that.
So essentially, the game is narrowing down your problem to fewer bytes by using encryption. So you basically need to keep track of fewer bytes where they are handled in wherever, memory, flash, hard disk, caches, and so on. And so this is the best thing that is currently available. And as we have heard, it's still not easy to do. But you basically shrink down the number of problem bytes in your architecture. So unfortunately, everything is getting really worse with Flash. Most of you use Flash daily in your digital camera. Flash has the property that it can be written only a limited number of cycles. So depending on type of Flash, you have something between 10,000 and a million write cycles that are can actually be done to a single Flash cell. So you have in Flash the property that if a Flash cell fails, it retains its data. Meaning that if a normal bit in memory fails, then you have a 50-50 chance that it is being stuck in the wrong or right position. So, but if a Flash cell or Flash block fails, it will retain your data. So reading will be still possible. The only thing that will not be possible is writing, meaning erasing your key, for instance. So as long as the stuff was only in your digital camera, the problem was not very pronounced. But what is happening now is that Flash is going into all kind of devices. What is beginning this year is that most major vendors are beginning to ship hard disks that have a Flash front-end cache. So where basically the disk cache on the hard disk itself that has been normal memory before is going to be Flash, and that is then used for all kind of interesting stuff, like Hibernate to disk will be Hibernate to Flash because it's faster to read and to write. And the problem escalates to most hard disks in notebooks that are sold in 2008 are projected to be Flash disks. So the price decrease of Flash, driven by MP3 players and everything, is so dramatic that you can today, if you just go to a shop and buy yourself a couple of 16 gigabyte USB sticks, you get into the price range that you have paid 3 or 4 years ago for the same amount of memory in a hard disk. So meaning if you really want to have a notebook that has no moving parts today, you can just buy that. So it's not really expensive. So Flash hard disks of 32 gigabytes are in the region of $300. So $400 if you want the really good stuff. So it is also going into all kinds of pre-buffers for RAID servers. So everything where stuff is cached and written and so on, Flash is going in there, and storage on basically all mobile devices will be Flash really, really soon. So all the mobile phones that you have, all the PDAs that you have are all using Flash. So that's the scope of the problem, which means that we need to think about now what needs to be done in software architecture for all the major operating systems that we're caring about to cope with this problem.
Well, Flash has an important property of if it's being erased, you usually use higher voltages to erase to pass the gate, which prevents electrons from coming out. Well, it's called floating gate, and so the higher voltage you use to write that memory also leads in to the memory being burned in more faster than in normal RAM. So you can find traces of the state you wrote there more easily.
Okay, since the number of write cycles is limited on any given Flash, let's say disk, what the manufacturers use is a mechanism that's called bare leveling. They put in like 10% or 20% or in so-called industrial grade flash even 100% of the listed storage onto the device, so that you have first redundant blocks as you have on your normal hard disk. So if your hard disk has failed blocks, then the hard disk logic will automatically map out to redundant blocks on the hard disk, and you will never notice until all the redundant blocks are eaten up. So in Flash, this is also being done. Typical values are 8% for the cheaper Flash memories, and then going up from there for more expensive stuff. So, but that's the relatively simple thing. So what can happen to you is for whatever reason your key is stored on Flash, you want to overwrite it, and of course your Flash memory will say, I have happily overwritten it, but in practice the key is still in the redundant blocks. This can also happen to you with hard disks, by the way. So if people doing hard disk forensics, what they always do is looking into redundant blocks to see if there's interesting information left there that could not be erased by the user anymore.
So basically, the idea is like in newer file systems that have copy on write. You store your secret and think, oops, I need to overwrite it. I mean, you use tools like SRM or whatever, and it writes 3 times crypto to the device and one times zeros. You have you're left with 5 blocks, one with your clear text, 3 times your secret, and 1 block 0 on the flash. And then this copy on write is fine for rollbacking, but is also fine for rollbacking if you don't really intend it to do.
Yeah, you can basically roll back into the redundant blocks. Yeah. And on top of that, the wear leveling mechanisms are something that the manufacturers of flash systems, that's basically most of their intellectual property except for manufacturing these flash modules is in the wear leveling mechanisms. Wear leveling means there's a logic in front of the real physical flash memory that sits in the flash controller that tries to level the load of write cycles over all the blocks in the flash memory. So basically it keeps a count on how many cycles have been written onto each block in the flash memory, and tries to make sure that each new write cycle goes onto the block that has the lowest write cycle count. So thereby maximizing the number of write cycles that can be done before the disk has to be declared broken. So these mechanisms are very rarely published, so there is very little documentation on how these mechanisms really work. There are some papers on them before the scientists are getting bought by SanDisk or whoever is currently making that stuff. And there are a number of techniques. For instance, one of them is called looking for hot and cold data, meaning looking for files that get frequently rewritten. And these are then more aggressively spread over memory blocks than so-called cold data that can be stored onto memory blocks that have already a high write count. So in order to maximize these the number of write cycles that can be gotten from the whole disk. So what it means is this flash controller is simulating to you something that looks like a hard disk. So there are even flash controllers now on the market for mobile phones that give you an FAT. So you basically have a FAT API into a chip. So basically you have a very thin driver layer in the operating system that speaks FAT to you, and that is just an API translator to the chip. And everything that's happening in the flash chip is more or less a black box, because there is no documentation on how to get in there. And there's also no raw mode, because they want to keep it really secret how they do their wear leveling and what they really do inside the flash disk. One of the reasons for these one of the reasons for this kind of behavior is that a lot of these manufacturers, for instance, M-Systems is one of the larger ones that has been recently bought by SanDisk. What they do is they buy flash chips from whoever sells them cheapest on the market. It could be LG, it could be Samsung, it could be Toshiba, it could be some company in China that we never have heard of. And they repackage these things into so-called flash modules that are ready to use for mobile phone manufacturers. And they then put in the flash controller that speaks correctly to the chips and speaks correctly to the mobile phone side, but you never know what is really happening in there. And so they can buy whatever is cheapest and sell their customer consistent product by just changing the software in the controller. So, which means flash forensics is currently something like a dark art, because what you need to do is you need to reverse engineer the flash controller. You need to find out what's happening in the flash controller in order to make sense of what the raw memory dump of the flash holds. So if people get a mobile phone into the forensics lab and they want to look for stuff that is still laying around, basically stuff that has not been erased by the wear leveling, then they look if they have the controller in the library and know how this controller works, or ask a bit around if somebody else in the community has this controller. And if not, then they need to sit down and reverse engineer the controller. And there are plenty of. So one forensics guy that I talked with had 26 really different types of flash controllers that he knew of that are being used in current products, with different wear leveling strategies, different means of talking to the flash chip, and so on. So this is basically good news. So the good news is that getting the data that has been left by wear leveling and the redundant blocks is relatively difficult. So if you cannot use for forensics the file system abstraction because you want to dig deeper, not just see the files that have been left around by FAT, then you need to know the flash controller. But given the amount of effort that can be spent by certain interested parties, this will not hold. So people are really sitting down doing this reverse engineering.
Still, I wanted to explain one of those algorithms, the hot-cold algorithm Frank talked about, has an interesting property of if it sees that one block is being used, not being written to for a long time, it copies the data from that block to another block which is has been more frequently written to, and thus reuse the lesser written to or fewer times written to block to this. On that way, you get copies of your data that you didn't even know about. Parts of your file system are being copied without you ever requesting that very file. So, and when you when you know that there is a FAT file system on an SD card, there's an important property of FAT. This is delete. Like you know from your old Windows days, just overwrites the first character in the file name, and the same thing happens on a digital camera. So if you think after borrowing an SD card from a friend, if you think erasing your SD card by your camera, really erases it, there's tools around. For example, Photo Rescue, the program the EDA guys write to make real money. That help you find important stuff, PDFs or JPEGs if it's accidentally lost. But if I borrow an SD card and my friend is interested in what kind of pictures I might have taken, he can use the properties of the FAT file system to reassemble the pictures.
Yeah, and the same then applies to flash memory on a lower level, only even worse. So if we look ahead, what will come around within the next 12 to 18 months, mobile devices will change. So rebooting a device is something that will not be as pronounced as it is today. So instant on, meaning you just open the device and can work, is a property that is highly desired by most users. So they don't want to wait. So this can be either done by Hibernate or even by executing from flash, or having memory deep frozen by certain techniques. But what that means is that the operating system is getting a more and more abstract view on the hardware that is below. So a normal flash hard disk that you can buy today is looking to the operating system like a hard disk, but it isn't. And in other words, the operating system of today has no security properties that can help us in the memory world of tomorrow. So people are moving more and more of their life to mobile devices, so there will be extremely thin and light devices that basically can do all your work except a heavy CPU load. And the companies that are doing the memory modules are of course preparing for that. One thing that is apparently coming up is a mode in the flash module that also holds the RAM in a mobile device that suspends automatically in hardware without the operating system doing anything the whole contents of the RAM into the flash. So it's just one pin that says sleep, and the RAM is written to the flash and powered off, and if you power on, the process is reversed. It's happening inside the chip.
And that includes kernel memory as well.
That includes all of the memory. So what happens is basically all your memory is being dumped on Hibernate onto a flash system where you have no real way of erasing stuff in there. So that is what is basically happening. So you, at any time when your device is powered down, or you to put it to sleep or whatever, you can essentially not know what is happening with the memory. So that means that the control over what is happening with memory is shrinking, except if the operating system is beginning to cope with that. So what is required essentially on a strategic level is that the operating system needs a go-to-sleep procedure that includes doing everything to make sure that no keys are lying around. So basically we need an operating system-wide notify procedure when the device is going to sleep, so that everything can be cleaned up from memory before the memory is being stored into flash. So that is currently not available. So I hope somebody will sit down and write that. But that's one of the most important things for the next 12 months, to build that into the major operating systems. Vista, for instance, has this suspend to flash on their hard disks that have flash built in, and they have done some stuff on that, but I'm not sure if that really will hold up against really looking deeply into the flash in there. So in other words, at the moment, security will cost you more battery. So because you're not using these really deep Hibernate, but you're only using suspend and trying to not leave your memory stuttering around your long-term storage. Yeah.
But also flipping your bits in memory costs battery time, and erasing the memory you've been using after, saying that free has to erase memory, so you have to all do it by yourself. You have to watch for yourself, the kernel will not do it. But there is ways to prevent your secrets from leaking. Well, that's using mlog in your application, encrypt your SPEP. You can, as I've told, flip the bits in memory. You have to be aware that any mass storage device you're talking to today will mean flash in one or the other way. So you have to consider that every data you store into mass storage needs to be encrypted. So there's no way around. If you accidentally write some secrets you better don't want to leak to a flash device, you can flood and pray. You can write gigabytes of data and hope that you finally hit the last block.
So, which is, by the way, the currently recommended method of erasing the SD card that you have borrowed from your friend, which is basically overwriting the SD card with a file that is larger or as large as the storage space on the SD card multiple times. So thereby hoping that you hit most of the stuff that you did on that SD card. So currently there's no other good way known, as long as the flash memory manufacturers are not coming around to offer in raw mode to write to the flash memory that gives the operating system control and says, okay, wear leveling can also be done by the operating system, which is, by the way, being done, for instance, on small-scale devices like DSL routers and so on. Basically, there is no real flash controller. They just write into flash memory and do some very rudimentary wear leveling without a real flash controller. But on the mass storage devices, currently there is no real raw access to the flash memory, which would be required to do things right security-wise.
Okay, there are some more ways. That would be nice if libc developers developers writing malloc would add hooks to allow memory being erased by free. So that it's overwritten if you don't need it, and if you take silent copies like in realloc, well, you should erase the old copy and not litter secrets around. So well, it's really hard writing around that. And well, as we said, would be nice if there would be security hooks into the kernel to allow dumping your keys. Well, it's not enough if the kernel dumps or forgets your secret keys. All applications must do so as well.
Yeah. So essentially, we hope that the flash manufacturers get some pressure from industry and from government, maybe from us, to allow lower level access to their products, so that we can get control, or that they provide secure erase methods, meaning that the flash controller offers ways to tag certain files and offer an erase function that says, okay, this file is really erased because we know on which flash blocks it has been written over time, and these flash blocks are then overwritten. So that wouldn't be difficult. But so far we haven't seen any pressure on the flash manufacturers to do that. So if you know somebody who works at SanDisk and so, or M-Systems or one of the other major flash controller manufacturers, then please talk to them. And in the meantime, we need basically to improve the operating system so that they can notify all applications and all kernel threads running that there is now an event happening that may yield, that may put all the memory onto a highly risky storage medium. So yeah, that's basically the only thing that we can recommend at the moment, or flood and pray. Yeah.
The most secure way would be to have no secrets at all and just live happily in a colorful world and slide down rainbows.
Okay.
So basically, that's all we have collected to tell you. Thank you for your attention. Any questions?
If one were to have direct access to the flash memory, there would be a need for a file system which does the wearables thing itself.
For instance, ZFS provides already a lot of the functions because they basically use this copy and write property anyway at the moment for rollback purposes, and that could be relatively easily be adapted to be a wear leveling mechanism if you want to write on raw flash. Thanks.